Welcome! In this video, we'll explore the partial fraction expansion or decomposition so that we can integrate a complicated single fraction or rational function easily. Suppose you are given the integral as shown. You'll probably want to try U substitution of this formula. If we make u as the denominator, x squared minus 5x plus 6, then what is the differential of u? du should be bracket 2x minus 5 dx. Unfortunately, there is no x term in the integrand. This means we cannot apply this formula directly to evaluate this integral. However, if we can rewrite the original fraction as a sum or a difference of two simpler fractions, then we may be able to apply the formula as shown. These simpler fractions are called partial fractions. Let's try to integrate using those partial fractions. The denominator u should be x minus 3 for the first integral and x minus 2 for the second. And both du's are just dx. Follow the right side of the formula to get the antiderivative of the original question is as shown. The process to change from a more complicated fraction to simpler partial fraction is called partial fraction decomposition. That is going to be the topic of this section. There are 4 cases to apply partial fraction decomposition. In all cases, we need to factor the denominators. For the first case, if the denominator has a linear factor ax plus b form, then use a constant on the numerator. In case 2, if the denominator has the repeated linear factors up to nth power, then we need to make n partial fractions with each exponent from 1 up to n. For case 3, if the denominator has a quadratic factor ax squared plus bx plus c form, then use a linear form on the numerator. Finally, for the last case, if the denominator has a repeated quadratic factors up to nth power, then we need to make n partial fractions, again with each exponent from 1 up to n, just like linear factors case. Let's practice setting up partial fractions without solving unknown constants. Please note that the denominators are all factored in this practice. However, you will need to factor the denominator first for the actual questions. For A, we see 2 different linear factors in the denominator. We can make use of those factors to set up some constant A over x plus 4 plus we also have the constant b over x minus 2. You may want to use a minus sign in between the partial fractions because the numerator has negative 3. However, we do not know the sign of a and b until we solve for them. So when you set up partial fractions, always use plus in between the fractions. For b, we can see that the x plus 5 term is repeated 3 times. When splitting this into partial fractions, we need 3 partial fractions containing increasing powers of the factor in the denominator. The first one should be a over x plus 5, like the previous example. plus, can you set up b over x plus 5 for the second one? This is not useful for us, since it is the same term as the first one. So the second one should be b over bracket x plus 5 squared, plus the last one, which is c over bracket x plus 5 cubed. This is the end since the original power is 3. How about C? X squared is usually treated as quadratic in algebra. However, for setting up partial fractions, consider x or x plus 2 as a linear factor repeated twice. So we need 2 partial fractions for each factor. Constant a over x plus b over x squared plus c over x plus 2 and d over bracket x plus 2 squared for the last one. Let's continue our practice on just setting up partial fractions. Now we'll focus on fractions involving quadratics. Again, for practice purpose, all denominators has been factored in this question. So keep in mind that you need to factor the denominator first in actual questions. For A, we see 2 different factors on the denominator. The first factor is linear, so we have some constant A over x minus 3 plus. However, the second factor is a quadratic, some linear factor bx plus c on top. For B, we can see 2x minus 5 factor is repeated 3 times. Therefore, we need 3 partial fractions. Since 2x minus 5 is a linear factor, the numerator is some constant a. The next one is a constant b over quantity 2x minus 5 to the square. The third one is c over bracket 2x minus 5 cubed. Since the power is 3, we are done with this part. And the other part, x squared plus 2x plus 5 factor is repeated twice. Since it is a quadratic factor, we use a linear dx plus e on the numerator. Similarly, fx plus g over quantity x squared plus 2x plus 5 squared. Since the power is 2, there are no more terms. Let's now look at an example to find out the partial fractions with unknown values. First, factor the denominator x squared plus 10x plus 21. Think of 2 numbers whose product is 21 of the last term and whose sum is 10, which is the coefficient of the x term. We can factor it as bracket x plus 3, bracket x plus 7. The order does not matter. You could also say x plus 7, x plus 3. These are not repeated factors. Let's separate it into partial fractions. Since the denominator has 2 different linear factors, we can make use of those to separate as a over 1 factor of x plus 3 plus b over another factor of x plus 7. Then we need to solve for unknown a and b. To do so, we need to create the basic equation. To begin, take the common denominator, which is the denominator of the original fraction. For the first term, we need to multiply the top and the bottom by x plus 7 and x plus 3 for the second fraction. Then multiply through by the bottom, so we no longer have fractions. The numerators of both sides of the equation is called the basic equation that is used to solve for a and b. Since we have the basic equation, we now need to find the constant a and b. Substituting the roots or zeros of x plus 7 or x plus 3 can help. The root for x plus 7 is negative 7, so substitute negative 7 into the basic equation and simplify and solve the equation to get b equal to 2. Similarly, the root for x plus 3 is negative 3, so substitute negative 3 into the basic equation again and simplify and solve the equation to get a equal to negative 4. Now that we have solved for a and b, rewrite the partial fractions with those values. Replace a with negative 4 and b with 2. So we have negative 4 over x plus 3 plus 2 over x plus 7 as the partial fractions. Let's look at an example involving quadratics. First, factor the denominator. We can see the common factor x squared. Let's take it out to get the form as shown. Here, we see the quadratic factor, so we could try to factor this part further. However, it cannot be factored, so we will keep it in quadratic form. Let's separate it into partial fractions instead. For the first factor, x is repeated twice. We have two fractions, so some constant a over x plus b over x squared. For the second factor is a quadratic, cx plus d over x squared plus 1. Now that we have set up the partial fractions, we need to solve for unknown a, b, c, and d next. In order to solve for unknowns, we create the basic equation. Take the common denominator, which is the denominator of the original fraction. For the first fraction, we multiply the top and the bottom by x bracket x squared plus 1, x squared plus 1 for the second one, and x squared for the last fraction. Then multiply through by the bottom, so we no longer have fractions. The numerators of both sides of the equation is the basic equation we are going to use to solve for the unknown values. Since we have the basic equation, we now need to find the constants a, b, c, and d. The substituting method is not efficient for these type of questions as obvious roots cannot be found easily for the quadratic factor except for x equals 0. You could still use the substitution method using any random x values to substitute into the basic equation. However, you cannot solve each unknown value directly, as you will have a system of equations. So I like to introduce the expansion method here. Keep the left side of the equation, and let's expand each bracket by distributing for the whole thing on the right side. Then gather powers of x together for x cubed term and c together, b plus d for x squared term, only ax for x term, and lastly, just b is a constant term. As you can see, there are all 4 different terms on both sides of the equation. Let's solve unknowns by equating the coefficient of each side. For x cubed term, take that term from each side of the equation, and they should be equal each other. Cancel x cubed from both sides to get the equation as 3 equals a plus c. Similarly, for x squared term, take each x squared term from each side of the equation and make them equal. Cancel x squared from both sides to get the equation 7 equals b plus d. In the same way, for x term, 2 equals a by cancelling x from each. And lastly, make each constant equal each other to get 4 equals b. From the x term, we know a equals 2 and b equals 4 from the constant term. Now we need to find out the values of c and d. Since we know a equals 2, substitute a equals 2 into the first equation to get c equals 1. Similarly, substitute b equals 4 into the second equation to find out d this time. We get d equals 3. Now we have solved for all the unknowns. We have solved for a, b, c, and d. We write the original rational expression using these partial fractions. Replace a with 2, b with 4, c with 1, and d with 3. Now we have found the partial fractions as shown. I hope this video has helped you in your preparation for integration by partial fractions decomposing method. If you like to explore integration by partial fractions, please watch the following video. Also, if you have questions, please write them on comment sections. Thank you for watching. See you again.